Hello, I am Vasilios Nakos, and I'm going to talk about fast and fold Boolean convolution via additive combinatorics. This is joint work with Carl Brinkmann. Given vectors u, v in Rn, the convolution with wraparound is a lengthened vector denoted by u star v, which satisfies the following equality for all I. Computing convolution is one of the most fundamental problems in computer science, across all computer science engineering, and it's known to be the same problem as polynomial multiplication, just in different vocabulary. Of particular interest inside theoretical computer science is the problem of Boolean convolution, for example, which appears as a computational primitive in many problems, such as subset sum, string processing, all pairs of the path, so on and so forth. So in Boolean convolution, u and v are 0, 1. The sum operator is substituted by a logical OR, and the product operator is substituted by a logical AND. And using sets, one can express Boolean convolution as the following problem. Given sets a, b subsets of n, then a Boolean convolution b, or a plus b, or a subset b, is the collection of all sums that can be attained by choosing one element small a in capital A and one element small b in capital B. It's known that one can compute a plus b in time over log n via fast Fourier transform. And this interpretation, this expression of Boolean convolution, this view, will be the one we will be adopting in this talk. Now let me go to another classical problem, or in particular to a variant of a classical problem, the modular subset sum problem. Given elements x1, x2, xn, and an integer t, all belonging in Zm, the goal is to decide whether there exists a subset of the elements xi which sum up to t. Okay, of course, this is a variant of the subset sum problem, but we're working modulo m, and it has a trivial algorithm as subset sum, which is in time m times n by dynamic programming. Or alternatively, in time mn log n, just mn log n, in time by using n-1 Boolean convolutions and computing the sum set 0, x1 plus 0, x2 plus 0, xn modulo m. Okay, so this is an n-fold sum set type of problem, as the title of the talk indicates. And furthermore, it can be solved in time near linear in m, in particular near linear in m plus n, but let me ignore the dependence on n now, by Axiotis et al. This was first on by Axiotis et al. In 2019, and subsequently by Cardinal and Diacono in 2021, and in parallel by Axiotis et al., including myself, in the same conference. Now, what's a crucial observation also? That all previous algorithms compute all attainable subset sums in time which is nearly near the size of the output. And thus, one can, for any t, decide whether there exists a subset easily after computing all attainable subset sums. Now, what is going to be our focus in this talk will be the following n-fold Boolean convolution problem with wraparound. Given sets a1, a2, an up to z subsets of zm, compute a1 plus a2 plus an. Of course, this is a subset of zn again, zm. This generalizes both modular subset sum and Boolean convolution. Okay. And the question is, can we have a principal approach for the more general case? So can we have an algorithm that solves not only modular subset sum and Boolean convolution, which are the interesting cases we know how to solve, but solve the problem in its full generality. And known fast solutions for the special case of modular subset sum do not use FFT, whereas we do not know how to solve Boolean convolution fast without FFT. So this means that we need a new approach other than the ones used in modular subset sum to solve this problem. Okay, because it has to simultaneously imply something nearly optimal for both modular subset sum and for Boolean convolution. Okay. Now, what's our main contribution? Given a1, a2, an, subsets of Zm, we compute a1 plus a2 plus an in Las Vegas k polylog m time and deterministic k times m to the little of 1 time, where k is the size of the input plus the size of the output, which means the following. This means that since K is actually the ideal goal one could have, one cannot compute this quantity faster than the size of the input plus the size of the output. Regarding Las Vegas algorithms, we are nearly optimal up to log m factors. And regarding deterministic algorithms, we are almost optimal up to this m to the little of 1 term. Now, one question is why the size of the input placed inside K? And the answer is the following, because A1, A2, and AN could be of size of cardinality on roughly m. And so the size of the input is m times n, whereas the size of the output can always be m. So it's not clear that the size of the input is larger than the size of the output. It's smaller than the size of the output, which is normally the case in modular substrate sum, for example. Okay. Okay, and for example, this immediately generalizes both modular substrate sum and Boolean convolution. In particular, modular substrate sum follows by setting all AIs to be of cardinality 2, right? Whereas Boolean convolution follows by setting n equals 2. And now let's proceed and see the toolkit that we're going to use. We're going to crucially be using the arithmetic structure of the subset operation. In particular, we're going to use something, a tool from additive combinatorics called Kneser's theorem. To set up Kneser's theorem, we need to define the symmetry group, which is the following. For a set X of subset of Zm, we define the symmetry group to be all the elements age, so that age plus X equals X, which means all the rotations, this contains all the rotations that bring X to itself. And this has a variety of interesting properties, which we'll see later, but Kneser's theorem is the following, that for two sets X, Y, subsets of Zm, then the cardinality of their subset is at least the minimum of cardinality of X plus cardinality of Y minus the cardinality of the symmetry group, comma M. Okay, these are first toolkit and most important. The second most important tool will be the following. Given something called sparse Boolean convolution, given A, B subsets of M, we can compute A plus B in time which is near linear in the size of the output. If we are interested in Las Vegas algorithms, and almost linear in the size of the output deterministically. And the symmetry group, the last tool, the symmetry group of X of a sorted set X can be found in time linear in X, the cardinality of X. And this is an application of Knuth-Moritz-Pratt. It can be reduced to pattern matching, which we won't talk about this in this talk. You can see the full version of the paper. And our goal would be to use Kneser's theorem to reduce the n-fold case to the two-fold case. And in particular, we're going to reduce n-fold sparse Boolean convolution to two-fold sparse Boolean convolution with the indication being on sparse. It's very important. We emphasize sparsity here. Okay. And now let's see our approach. Let's see an overview. Let's try to compute A1 plus A2 plus A3 plus A4 plus A5 plus A6, so on and so forth. And let's try to do this in a tree-like fashion, which means compute A1 plus A2, then compute A3 plus A4, then A5 plus A6, so on and so forth. And then start combining the answers. Take the answer A1 plus A2 and combine with A3 plus A4. So this creates a full binary tree, if n is a power of 2, in which each node of which contains a sum set operation. Okay, sounds very reasonable, pretty standard. Now what's the case? For any two sets X, Y that are going to emerge in this process, at some point we compute X plus Y. And we check at that point whether the cardinality of X plus Y is smaller than the cardinality of X plus the cardinality of Y minus 1. And now what's structural insight? Kneser's theorem says this interesting inequality, states this interesting inequality here. Okay, what this means? This means that if X plus Y is smaller than the sum of x and the sum of y minus 1, and of course, x plus y is not the whole group, then the symmetry group of x plus y is non-trivial. What does this mean? The symmetry group of x plus y being non-trivial. One can check that this implies some sort of periodicity condition. And in particular, it implies that there exists a divisor of M, let it be D, and the subset Z prime from 0 up to D minus 1, such that x plus y is Z prime plus D times Z of M over D. So, in other words, to get x plus y, there's a set Z prime from 0 to 1 D minus 1, and then x plus y is Z prime union Z prime plus D union Z prime plus 2, Z prime plus 2D, so on and so forth. Okay. So this says that x plus y is periodic with period D, which is good because we can apply some sort of recursion, as we shall see in the next slide. Okay, let's recall, we try to compute A1 plus A2 plus A3 plus A4, so on and so forth in a tree-like fashion. We perform, let's say, sparse Boolean convolution in each node, a sum set operation. And if we're in the state that, in the situation that the cardinality of x plus y is small, this implies that the symmetry group is non-trivial, is at least 1. Now, one can check that if the symmetry group of x plus y is at least 1, then the symmetry group of the sum set, the whole sum set A1 plus A2 plus AN is at least 1. I will talk about this later. Okay, so this means that if at some node, during the execution of the algorithm, the symmetry group is non-trivial, turns out to be non-trivial, then the whole sum set has a non-trivial symmetry group. Okay. Which in turn means that A1 plus A2 plus AN is periodic, as stated in the previous slide. So if A1 is plus A2 plus AN is periodic, which is what we want to compute, then we should recurse, right? And how do we do that? We compute the symmetry group of, let's say, x plus y, using the third path from the toolkit. And we know that A1 plus A2 plus AN equals A1 plus A2 plus AN modulo D plus a number of copies of Z M over D. Right? This is what it says. And now what does this equality exactly here say? It says that, look, you can apply recursion now, and you can reduce your problem to a universe of smaller size, where D is a divisor of M. Okay, which means progress. Okay, now of course, one thing to do is that we never arrive at a situation. Meaning we never find two sets x comma y such that x plus y in cardinality is smaller than the cardinality of x plus the cardinality of y minus 1. If this does not happen for all derived pairs x comma y, then we can show that when the computation arrives at root, we can bound the total size of all the intermediate subsets by roughly k, which is the size of the input plus the size of the output. This is an oversimplified explanation, but I'm going to leave it out for now and see the paper. And in particular, the idea is the following, that using a sparse convolution routine in each node, the running time of the algorithm obeys up to log m factors the following recursive relationship. T of k comma m equals T of k comma d plus tilde k. So the left-hand side is the running time to solve the problem with size of input plus size of output pk, and over a group of size m. On the right-hand side, we have the first term corresponds to the possible recursion, and the second term corresponds to all the operations we have done so far. Of course, implementing all these things is somewhat more complicated than I'm saying in this talk. I'm kind of oversimplifying, but please go see the paper for all the details. But I'm just giving an overview. And since this is a divisor of M, can make D to be at most m over 2, actually strictly. Yeah, we can always ensure that D is at less than m over 2 and have the equation solved to tilde k. Okay. And of course, now we need to have some crucial lemmas for the symmetry group that allow this whole argumentation to go through. Okay, now one lemma that we need to say is that, look, if H belongs in the symmetry group of x plus y, then H belongs in the symmetry group of x plus y plus z. Why do we need this lemma? Because recall that A1 plus A2 plus AN is x plus y plus something else. And we know that the symmetry group of x plus y is non-trivial. So we need to say that the symmetry group of the whole subset A1 plus A2 plus AN is non-trivial. Which means that the lemma we need to prove is exactly this lemma shown here. And this actually has a very simple proof. Because H plus x plus y plus z equals, let me put inside parentheses H plus x plus y, and outside of the parenthesis z, then H of x plus y equals x plus y, and we're here. Okay. So in order to find, let's say, not to find D, which is the universe we're going to reduce to, it suffices to consider only the symmetry group of x plus y rather than the symmetry group of x plus y plus anything else, which gives A1 plus A2 plus AN. Okay, and lemma 2, if x subset of Zm satisfies the symmetry group of x being larger than 1, having a non-trivial symmetry group, then for D in symmetry group of x, we have that x can be written in this expression, in this periodicity expression, has this periodicity expression. And this is not particularly hard to show. One can show that trivially, actually, by the notion of the stabilizer, because D belongs to the symmetry group of x for any small x and capital X, small x plus D, small x plus 2D, small x plus 3D, and so forth belong to X. So you can find a J such that small x plus J times D can be brought down to 0, D minus 1, in which case it equals exactly X modulo D, right? And this will give us actually precisely the set, essentially Z prime in the previous slide. And then we, by some more, if you think about it a bit more, then you can see that X has exactly this property because you can add any multiple of D to X modulo D and still remain inside X. Okay. And for the rest of the talk, I'm going to talk about twofold sparse convolution. And I want to make a recap here. What was the idea? The idea is to compute A1 plus A2 plus A3 plus A4 plus AN in a tree-like fashion. If some subset, at each node we have a subset operation, a sparse Boolean convolution operation, right? If the subset does not grow as desired, then there's a non-trivial symmetry group, so we can recurse this progress. Otherwise, we can ensure that when we arrive at the root, when the computation arrives at the root, we're in good shape in the sense that the total size of all subsets appearing in this process can be bounded in in a near linear way by K. Okay. What now? Of course, this leaves out some details, which we will see in the paper, some implementation details, some non-trivial implementation details, but I'm just giving the rough overview. And of course, what we need now is a way to perform a sparse convolution, right? Because that's what we perform in each node in this process. And efficient sparse convolution do exist. So here's the theorem that we prove in this paper. Given sets A, B subsets of M, we can compute A plus B in Las Vegas time, which is near linear sensitive, and in deterministic time, which is almost linear. Okay. In A plus B, it's in the cardinality of A plus B. So it's the cardinality of A plus B times M delta law of 1. And for that, we're going heavily to depend on a theorem of Chern-Levenstein from 2015, which is the following. Given sets A, B such set of M, and a set T, which is satisfies the following, it's a small superset of A plus B, then we can do what we want. That's what the theorem of Chern-Levenstein proved. Okay, so it's given additionally a promise set T, which is slightly larger than the support, but can contain all of it. And they show how to solve sparse convolution. And in this paper, we show how to remove this assumption on T. And how do we remove it? We gradually build a subset. That's a crucial idea, which means the following. We consider the folded versions of A and B, which what folded means for us means that we consider A of L to be A mod 2 to the L for some L, and B of L to be B mod 2 to the L. Now know that we're working over the integers because as I said before, twofold sparse convolution over the integers and the LZM are computationally the same. So let me assume that I'm working over the integers. So this thing makes some sense. A mod, yep, okay. And the crucial observation is that A of L plus 1 plus B of L plus 1 is essentially contained of A of L plus B of L some set, a small set, right? This is the crucial observation. So in some sense that I can control AL plus 1 plus BL plus 1, the subset, given a lower order subset, A of L plus BL. And the idea now is to compute AL plus BL recursively and then find AL plus 1 plus BL plus 1 by setting T to be this set. Once I set T to be this set, I can run Chern-Levenstein on AL plus 1, BL plus 1, T on this triplet. I'm exactly in the setting of Chern-Levenstein. Okay, so this is a trick which takes any algorithm which can solve promise sparse convolution and removes the assumption of the promise. Okay. And at the end of the day, we only need to output A log M plus B log M or A 2 log M, whatever, plus B 2 log M. Okay, so that's it. Now let's recap. We can solve n-fold Boolean convolution in Las Vegas time near linear and K. It's the size of the input plus of the output. This generalizes both modular spread sum and Boolean convolution using new ideas and a different approach than modular spread sum, crucially different. And the main new tool was to exploit the rotational symmetries of the DEM via Kneser's theorem. Additionally, using sparse convolutions plus some other string processing machinery to handle the symmetry group. And that's it. Thank you.